Hello everyone, this is Sir Brian Orlasan Cordova. So today's topic is about continuity of functions. So we will continue the discussion about the limits of functions. So before that, we need to understand the behavior of functions as it approaches a limit. So we need to first discuss about one-sided limits. So the behavior of the function approaching a limit from one side. To have a limit L as x approaches c, a function f must be defined on both sides of c. So if a graph of a function defined on both sides of c, its values f of x must approach L as x approaches c from either side. So on one side, we have the right-hand limit. So the limit of the function f of x as x approaches c from the right is equal to L. Given a graph of the function f of x, as x approaches c, it approaches the value L. This means that each x involved is greater than c, as x approaches c from the right. On the other side, we have the left-hand limit. So the limit of f of x as x approaches c from the left is equal to L. So from the left, the graph of the function f of x as x approaches c approaches the value m or L, which is the limit from the left side. So this means that each x involved is less than the value of c as x approaches c from the left. Example. Given the function f of x is equal to x over absolute value of x. So this is the graph of the function y is equal to x over absolute value of x. We will take its limit as x approaches 0. So as x approaches 0 from the left, the function approaches the value of -1. And finding the limit as x approaches 0 from the right, it approaches a value of 1. Since this function approaches two different values, so the limit of the function x over the absolute value of x as x approaches 0 as a whole does not exist because there are two different values approaching, not a single value L. Now we can talk about the continuity of the function. The continuity of a function, so the function f is continuous at x is equal to c if the limit of the function as x approaches c is equal to the function value f of c. And it is right continuous at c if the limit of the function as x approaches c from the right is equal to the function value f of c, and it also left continuous at c if the limit of the function as x approaches from the left also equal to the function value f of c. So given a graph of a function y is equal to f of x, which is defined on the interval a to b, and as x approaches a from the right, it has a continuity from the right because the function approaches the value of f of a. And as x approaches b from the left, it has a continuity from the left since it approaches f of b. And if x approaches c from the right, we have continuity from the right since it approaches the value of f of c. And if x approaches c from the left, it also approaches the value of f of c. So as x approaches c for both sides, we have the two-sided continuity. Since we have two-sided continuity, we can say that the function is continuous at c. To know that a given function is continuous, we're going to use the continuity test. So a function f of x is continuous at a point x is equal to c if and only if it meets the following three conditions. Number one, we have the function value f of c exists, meaning that c is in the domain of f or f of c is defined. Number two, we have the limit of f of x as x approaches c exists, meaning that the function has a limit as x approaches c. And lastly, we have the limit of f of x as x approaches c is equal to the function value f of c, meaning that the limit is equal to the function value f of c. Properties of continuous functions. If the functions f and g are continuous at x is equal to c, then the following algebraic combinations are continuous at x is equal to c. Number 1, sum of functions f plus g. Number 2, the difference of functions f minus g. Number 3 is the product of a k, where k is a constant real number, times the function f. Number 4 is the product of functions f times g. Number 5, we have quotient of functions f over g, provided that the function value g of c is not equal to 0, since it will become undefined or indeterminate. Number 6, we have nth power of function, where n is a positive number. And lastly, we have the nth root of a function, where the index of the root is a positive, provided that the nth root is also defined on an open interval containing c. Example, limit of the sum of the functions f of g of x as x approaches c. And from the theorems of limit using the sum rule, this is equal to the sum of the limits of the function f of x and limit of g of x as x approaches c. And since f and g are continuous at x is equal to c, so the limit of f of x as x approaches c is equal to f of c, and the limit of g of x as x approaches c is equal to g of c. And from the properties of functions, we have f of c plus g of c, which is equal to sum of functions f plus g of c. We can see that limit of the sum of functions is equal to the function value f plus g. Thus, the sum of functions is continuous at x is equal to c. Then we have limits of continuous functions. If g is continuous at point b, and the limit of the function f of x as x approaches c is equal to b, then the limit of the composite function g of f of x as x approaches c is equal to the function g of the limit of f of x as x approaches c, which is also equal to g of b. Example, find the limit of function 3u squared as x approaches 3, where u is equal to x plus 1. Solution, let g of x is equal to 3u squared and f of x is equal to x plus 1. And since the limit of f of x as x approaches 3 is equal to the limit of x plus 1 as x approaches 3, evaluating the limits, we have 3 plus 1, which is 4. So the limit of f of x is 4. Then the limit of g of x as x approaches 3 is equal to the limit of 3u squared as x approaches 3 is also equal to the limit of 3, substituting the value of u, which is x plus 1 quantity squared as x approaches 3. Then substituting the limits of f of x, which is equal to 4. 3 times 4 squared, we have 48. Then we have continuous extension to a point. So given functions with limits at a point where it is not defined, so meaning these functions are not defined on a certain point. If f of c is not defined, so meaning the function f is not continuous at c. But the limit of f of x as x approaches c is equal to L exists. To get a continuous extension to point c, we are going to introduce a new function, capital F of x, which is equal to the original function f of x if x is in the domain of f, and it is equal to 0 if x is equal to c, since c is the point where f of x is not defined. Therefore, capital F of x is the continuous extension of the original function f to x is equal to c. For example, show that the function f of x is equal to x squared plus x minus 6 over x squared minus 4, where x is not equal to 2, has a continuous extension to x is equal to 2, and find that extension. Since this function is not defined on x is equal to 2. So we're going to find a continuous extension to that point. So given the graph of the original function, we can see that at x is equal to 2, we have an open circle on the graph, since at that point it is not defined. So that point is not included on the graph. Now, as a solution, we can transform the original function, since the function is reducible, by factoring the numerator and denominator and cancelling out a common factor. So now the new function would be x plus 3 over x plus 2. So to verify that this function is now continuous, we can take the limit of the function as x approaches 2. So substituting the values of x is equal to 2, we have 2 plus 3 over 2 plus 2, which is equal to 5 over 4. So the continuous extension of the original function is the new function y is equal to x plus 3 over x plus 2, and the limit of this function as x approaches 2 is 5 over 4. So as a special topic, we have the intermediate value theorem. The intermediate value theorem, if x is a continuous function on a closed interval a to b, and if y sub 0 is any value between f of a and f of b, then y sub 0 is equal to a function value f of c for some value of c in the interval a to b. The intermediate value theorem says that any horizontal line y is equal to y sub 0 crossing the y-axis between the numbers f of a and f of b will cross the curve y is equal to f of x at least once over the interval a to b. So as an example, to prove that the equation square root of 2x plus 5 is equal to 4 minus x squared has a solution. We can graph this given equation of intersecting functions, where the left side is equal to y is equal to square root of 2x plus 5 and the right side is equal to 4 minus x squared. So their intersection would be the solution for the equation. As a solution, we can rewrite the equation by transposing negative x squared to the left side. So we can now have an equation with two functions, square root of 2x plus 5 plus x squared, and a linear function y is equal to 4. So the left side of the new function, so the left side of the new equation is equal to a function y is equal to square root of 2x plus 5 plus x squared. And the right side would be our y sub 0, which is equal to 4. Then we can set this new function on the left side of the new equation as f of x, and we can subdivide it into two functions where g of x is equal to the original left side of the original equation, square root of 2x plus 5, which is continuous on the half-open interval from negative 5 over 2 up to positive infinity, including negative 5 over 2. And h of x, which is x squared, which is continuous for all values of x. Now, f of x is the sum of g and h is also continuous on the half-open interval negative 5 over 2 up to positive infinity. Since this interval is too large, we need to find a new interval where f of x is defined. By trial and error, we have f of 0 is equal to square root of 5, which is approximately 2.24. And f of 2 is equal to square root of 9 plus 4 is equal to 7. Note that f is also continuous in the closed interval 0 to 2. Since y sub 0 is equal to 4 is between f of 0 and f of 2, approximately 2.24 and 7. By the intermediate value theorem, there exists a value c on the closed interval 0 to 2 such that f of c is equal to 4, which that value of x is equal to c solves the original equation. So it is actually the intersection of the original functions. And that's all for today. See you for another lesson.